Hey, welcome back to Yield Foundry. This video is going to be touching on some of the materials that we used in the foundry to maintain and repair either our ship or ships that were alongside. But, you know, we were a destroyer tender. Well, I was on a sub-tender, and then one of the 3 destroyer tenders. So mostly, you know, I was on destroyer tenders, and destroyer tenders would have ships come alongside, not just destroyers. They could be cruisers, they could be destroyers, they could be tugs, they could be almost any ship that actually floats on water. And they might put in a job order to have, you know, replacement dogs on a watertight door to be made, and I'll show you what that is in a bit. They might put in job orders to have wheels that was on a valve to be made. You know, people lose things, people put too much stress on things and break them, and they don't have any foundries on those small ships. My ships, most of them were the older tenders, and they were about 50 yards wide by 50 feet wide by about 449 feet long, thereabouts. And you know, we had everything on the ship that you could use to repair whatever you can think of. Okay, and well, for the foundry, we had all these different little jobs come in that we usually had a pattern made by the pattern shop, and we would ram it up and pour them and you know, send them down to the machine shop for final machining. Then they would be given to the people who put the job order in. Okay, pretty simple system, pretty easy, not that bad. For our most general purpose metal that we used, now I take away the name best, or the description best, because there's metals out there that can fit perfectly like a puzzle piece in a jigsaw puzzle, this specific thing that you need to be made. Okay, it has to have a certain amount of tensile strength, the kind of strength that you would have to exert if you wanted to pull something like this directly apart. Okay, that's tensile strength. Compression strength would be as if I tried to put too much pressure on this and it would fracture by my compressing it. Shear strength would be if something came across and hit it on the side and, you know, sheared it off, right? There's all kinds of different ways to measure the types of strengths of different metals. Well, we'll stay around tensile strength this time, because that's, most everybody can get an idea how much it would take to try and pull something apart by pulling it, like a chain. How much would you have to use, how much force would you have to use to pull a chain apart? Okay, that's how much tensile strength you would need to pull that chain apart. Okay, there's other people who would argue that that's also shear. That's also, you know, different other types of strengths. But I'm staying on tensile strength right now. Gunmetal, or rather tin bronze. Now that's how you ordered it in the Navy stock system. Tin bronze, also known as gunmetal bronze, is the principal bronze that we use to make just the oddball thing that they needed to have made on board our ship or on board other ships that put in job orders for it. Now, why did they call that gunmetal bronze? Well, because it's as close as possible, not on purpose, but it's the closest thing that you can come to the alloy that they used to make the cannons on board the ships back in the 16s and 1700s. Okay, those cannons that are taking the archaeologists, underwater archaeologists, are taking from the bed of the seafloor. That's basically the material that they used to make those cannons. Okay, so that material has its I don't know, nickname you might call it, gunmetal bronze. Okay, now gunmetal bronze, pretty strong bronze. I mean, it's not as strong as brass is. Brass, in many cases, is considerably stronger than bronze, but brass is more expensive because of the materials that that's made of. So we stayed around the least expensive multi-purpose material, which was gunmetal bronze. Now, I'm going to show you some pictures here just in a minute, and so I can give you an example of some of the general things that we used to make out of gunmetal bronze. Okay, and the first one I want to show you is just a kind of a conglomeration of different parts that I found, and all these are covers and wrenches and all kinds of oddball stuff. But you can see that they're a copperish instead of a yellow. They're a copper colored material, and that's generally how you can identify bronze versus brass. Brass is usually a very light, a yellowish, golden kind of material. And that's how you can identify those. Okay. Now, keep in mind all these pictures that I'm going to be showing you, I got off, the internet, and basically I just wanted, I said bronze castings, and they gave me pictures of bronze castings, and they, a lot of them were great, come in handy. Some of them are smaller when it comes to the picture, so you'll have to squint a bit, but some of them are plenty large where you won't have to worry about it, about seeing it. Principally, most of the stuff I remember making in the foundry were replacement dogs for doors. Now, what's a dog? Okay, I'll show you. Here's a watertight door. I'll show you two of them. Kind of an older one that had to have been on a ship that's either very poorly maintained or was just old, because the form of the door just reminds me of the ships I used to see that were in the 20s and the teens, 1920s and teens. Those items you see on the periphery or on the outside edge, those can be moved with your hand. You turn them all away from the center of the door, and you do it all of them, and you can open the door. If you close the door, you would turn the handle towards the center of the door, and if you close them all, then they are tight, and they're tied down tight and being pressed against a rubber seal that won't allow any water through it. Like if you were certain parts of the ship was flooding, you had all those doors shut, the flooding would only take place in the compartment in which it's isolated because of watertight doors. Now here's a more modern watertight door, the kind that I was used to seeing all the time on board my ships. You can see where they went and put the dimples or depressions in the door. Basically, all that was just to make the door a little stronger. Okay, those on the outside edges of that door, aside from the hinges that you can see, those are dogs. We dog them down tight. They press against a big rubber gasket on the inside, and against the knife edge, and and that will be pressed, and then now it'll be watertight. No water can come through it, unless it's like really, really unusual circumstances, like a huge amount of water coming through, pressurized water. So those are only two. Those are the kind that we made most of the time. Sometimes we made dogs for ammo boxes, or rather ready service lockers that had ammo in them. Those were in many cases nothing more. It looked like a lollipop that we would make, and the machine shop would take them and put threads on the long part of the lollipop, and then drill a hole in the round part of the lollipop, and then that would be installed in the on the outside periphery of the locker, and then on top of it, to to tighten the locker lid down, it would be a what looked very much like a thumb screw, okay, that kind you could buy in a store, and they would tighten them down, and no water could get in. That you wouldn't have any corrosion inside, and it'd be very hard for the environment around it to ruin the ammunition that we needed. Okay. Here's a picture of what's called a bronze dog with a shaft that goes through the door. You know, that's a good example of the things we used to have to make. And then here's another picture of a very old piece of equipment that was on a ship. It was an indicator plate, and we used to make those also. And that you would look at that and you would see it either up in the bridge of the ship where they're doing the navigation and steering and all that, or you'd find it maybe back in the rudder compartment, where that would also show what position that the rudder was in. I'm trying to recognize and see. I might not be right on that being a rudder indicator, but you see, you know, if you've been in the Navy, you'll see it and you'll know what that is. Well, we used to make those things also, not just the plate that's being shown there, but that indicator was some of the stuff we used to make also. Now, and that was you know, in the 1920s when we first were, you know, established as a rate in the Navy. And you know, the ships back then were you know, okay, but they were not quite as sophisticated as we wound up needing. As our missions changed, we needed more equipment, we needed better equipment. We you know, a lot of the safety stuff we had on board was not good enough. Like, for instance, if the Titanic had watertight bulkheads and watertight doors, like the Navy has watertight bulkheads and watertight doors throughout the ship, if the Titanic was like that, it would probably have listed to one side where the water got into that compartment, and then the rest of the ship would have been saved, and they would have limped into New York City or the nearest port that they could fit in. As it was, when the side of the ship was ripped open by that iceberg, the water progressed from where it entered first, went from compartment to compartment to compartment, and because it hit the ship at the forward, I think starboard side, forward starboard. Well, let's just pretend it's starboard, and it just started. Let's say this is the ship. It just started getting water, more and more and more water, until everything started being pushed under. As soon as it got to a particular angle, the after portion of it broke off, because, you know, this wasn't strong enough for the weight of the after part of the ship. It broke off, hit the water, sank, and the rest of it sank. Watertight doors keep the water from progressing from a damaged portion of the ship to an undamaged portion of the ship and save the ship. And that's why it was important that we always kept up on our watertight doors. As the ships became more and more sophisticated, they became bigger and bigger. They were able to do more and more of the different types of jobs. The equipment down in engineering and throughout the ship, you know, engineering type equipment throughout the ship became, you know, there was more and more of it. Okay, a lot of the pumps, rather most of the pumps that pumped potable water, seawater, steam, and so forth and so on, they were basically in the engineering compartments where everybody could keep eye on them and keep them maintained easily. Now, but throughout the ship, you had piping systems that went from fore to aft, and from the lowest portion of the ship to the highest portion of the ship. And each one of those had to have a valve spaced ever so, you know, evenly spaced, so that during battle, if a bullet went through, let's say, a piping system that had salt water coming in it, you'd have to isolate that piece of pipe where it was busted by closing the nearest aft valve and close the nearest forward valve, so that was totally isolated, and you had no more flooding taking place until damage control could get over there and repair that, and then those valves could come back open. If it was irreparable, many times they would have a capability of rerouting that water and put the ship back in operating condition. So they, of course, it fell to the foundry when they started putting in more and more valves, that the foundry would have to start replacing valves that got broken, and the vast majority of the valves, of course, were made in the civilian sector when they were making the ship. Okay, there were a lot more people that were making in bigger foundries and making all kinds of valves. Well, it turns out when we started getting the jobs, we were making valves just like we were making anything else. Pattern makers would make the patterns in the core boxes. We would make the molds and the cores, and we would pour it at the proper temperatures. Machine shop would machine all the stuff they needed to machine, but before they would put it into operation, it would go into a testing procedure, a hydrostatic testing procedure, where they would blank off the flanges, fill it full of water, and then put a pump on it and bring it up to, I don't recall exactly what the criteria was, but let's just say 1 1/2 times the operating pressure of the piping system. Well, they started doing that, and they found out that there was pinhole leaks in the metal. Okay, what looked like a very nicely made valve with no defects in it, no sand, no dross, no slag, nothing in it, in the metal anywhere. All of a sudden they had anywhere from just let's say imagine this is the edge of the valve body. Suddenly there's a tiny little drop right here. The drop gets bigger, and it goes down and falls to the ground, and another drop is forming. It's not necessarily a cascading affair. But it's leaking by somehow. It's leaking through this metal wall. Okay, well, the metallurgists and the foundrymen of the time said, hey, there's a problem here, we need to investigate. So what they wind up doing is they wound up cutting these valves that were leaking, and much to their surprise, they found that there were voids in the metal. Okay, despite the fact that you had maybe you put a couple of risers on those flanges, which would have naturally been somewhat thicker than the wall of the valve. Despite that fact, still voids were forming. Okay, now how could that be? Well, first, if you went and looked at the video that I put out, the name of which was Designing and Using Risers in the Mold for Your Castings, you will have been able to see how I described how molten metal solidifies into dendrites. The dendrites grow into crystals. The crystals grow until the crystals can take no more, the sizes that they can make, and then they use up all the metal or molten metal, and the crystals solidify totally where they can't grow anymore. Okay, well, I explained that in better detail than I'm going to now. So if you want better detail, please go to that video about risers. Now, let's pretend you've just poured a casting, okay, and it's an engineering type casting, whether it be a pipe fitting or a valve or pump body, or or any of the one of those, maybe even just the lid to something. Okay, you don't want those to leak by any more than you want any pump body to leak by. Okay, none of that's any leaking. Leaking is bad. Water getting into the inside of the ship is bad. So no leaking is allowed. Okay, you've just poured your casting. You're done pouring. As soon as the metal started touching the inside of the mold cavities, they started growing little tiny crystals, and the very outside edge is the smallest crystals because they formed and solidified almost immediately. The next set of crystals on the next lining of that casting is the crystals are a little bit bigger than the first ones. If there's another layer, there's a little bit bigger than the second layer, and so forth. Now, if you have, I'm going to continue with the explanation first. What's formed first are dendrites. Okay, dendrites, basically, if you were to look at a snowflake real close, that's a group of dendrites that have grown out of the middle where the ice started accumulating. Okay, but dendrites is the same form. Metal will go, and here's a picture of dendrites. Metal will grow again, first from the outside edge, wherever the metal is touching the mold cavity first. That's where everything will freeze up first, and then it'll continue to draw from the molten metal until all the molten metal is gone. Okay. Many cases, the molten metal isn't sufficient to fill in those in between the skins that they're forming down in the middle here. They don't fill them all the way up. Okay, so what you're going to wind up having is some voids in here, in between the skins. Now here, I'm going to show you some valves, the kind we most of the time use on board the ships. And those valves in anywhere in those the valve body, there could be developing, or have developed, a leak because of those voids. Now, I don't have very many pictures of the dendrites. I show you a first picture of a dendrite. I'll show it to you again here. And that looks like a pretty solid area, right? Doesn't look like there's much of anything that can flow through that kind of stuff, right? But here's another picture of dendrites, and you can see that in between the dendrites there are voids that have filled, or rather that have formed. Okay, here's a picture of bronze dendrites, and if you look close, you can see where there are holes. Everywhere else it's very, very solid, very, very tight, but there are holes, those black portions of the picture, that have formed during the solidification process. Okay, so what do? How can you fix that? Well, some genius guy back then said, hey, why don't you just add some lead? And I will explain to you what he meant by that. Now, I'm going to pick you up, and I'm going to turn you around to the whiteboard, and I'll start explaining things. Gunmetal bronze. The formula for gunmetal bronze, and by the way, I made this in the foundry too, and what this used to be before I made it out of bronze was a plastic knife that you found in the store for the kids to play with. Okay, easy to make, kind of just a neat little thing to have. All right, now I'm going to turn you around, and I very much hope that we don't have too much reflective light here. turn you around. I'll try to keep you at a little bit of an angle. Okay, tin bronze or gunmetal bronze is made up of 88% copper, 8% tin, no lead, and 4% zinc. Now, when I said, you know, I found out that we use that most of the time, I said, well, why don't we just use steel? Well, steel is pouring steel, melting and pouring steel is a whole different world. Okay, so many more things you have to do, so many more bits of equipment and supplies that you have to buy to make good steel. And besides steel, there's a million of them. There's a million different types of steel. I mean, even in mild steel, there's all kinds of different types of mild steel. But mild steel was the only thing we could compare tin bronze against a steel. Okay, and mild steel being one of the lesser when it comes to tensile strength materials. So well, let's just say it was the weakest steel that we can compare against tin bronze. Okay, mild steel has, its tensile strength, in the case that I found, one of the lowest tensile strengths was 58,000 pounds per square inch. Okay, it would take 58,000 pounds per square inch to pull mild steel apart. All right. Well, we couldn't work with steel very much on board ship, but what we did use, of course, like I said before, was tin bronze. Tin bronze was 45,000, and in some cases I read 40,000 pounds per square inch tensile strength. 58, 45, hey, that's pretty good for a bronze. So they used it a lot, and if they ever broke, it was because somebody usually used a hammer on it and knocked it apart. Okay. Now, they found out that those valves were leaking by. Somebody said, hey, let's go ahead and put some lead in there and see what happens. I'm sure they tried any and all other ways of trying to improve the material, like temperature, pouring temperature changes, and maybe adding a little bit of more zinc or any of that. And apparently that stuff didn't work. So they decided to try lead. Okay. Now, there's another bronze that we used in the Navy. Not very often, but we still used it because we didn't very often make, valve bodies. But this stuff was called leaded tin bronze. Okay. Its nickname, or its common name, was valve bronze. Now, valve bronze, leaded tin bronze or valve bronze, was the same copper as tin bronze, just a little bit less tin, but they put in 2% lead, and the zinc stayed the same. All they did for leaded tin bronze is add only 2% more lead. Okay. Now, how is that supposed to improve anything? Well, what's called the solidus temperature for bronze, or the temperature at which bronze fully turns solid, is about 1570 degrees Fahrenheit. Okay. But the solidus temperature for lead is 621. Okay, it's like less than half of that. So when all the bronze has solidified into all the bronze crystals, the lead is still liquid. Okay, and you've mixed it throughout the mixture, or rather the alloy. So the lead is going to be in the place where that void may have was made, or may have developed. Okay, so now those voids, because of that lead, are no longer voids. What they are is gunmetal bronze with places where they have the lead encapsulated by the bronze, and eventually, once the whole casting gets below 621 degrees Fahrenheit, the bronze, the lead will have solidified inside there and plugged up all those voids. Okay. Now, even if you have pipe fittings or have other things, like for instance a pipe fitting. This is my crude design of a pipe fitting. Let's say this thickness here, which is the same all the way around back, both of these. Let's say this thickness here is the same thickness going through the body. As a molder, you wouldn't need to put too much of a worry on any kind of risering. Okay, I would still probably put a couple of wedge risers up there just to fill it in, just in case we accidentally pour it too hot, because you can pour your metals too hot, and in a casting that normally wouldn't have developed a shrink, if you're careless enough to pour it hotter than you needed to, you'll have developed a shrinkage. And if you didn't put a riser to fill in that shrink, you'll have to do the whole job all over again, and sometimes that's a couple of days of work. You can do the same thing for a plate. If it's a plate that's uniform thickness, you just fill it up, and it'll and you pour it at the right temperature. You won't have any shrinkages in here. But what you will have, if you cut that in part, you will have a void that will have because you ran out of material to solidify all the way to the center, all the way from top to bottom, side to side. You're might have a void right there in there where it's all the liquid bronze will have already solidified, and there's no more to feed it. Okay, so it was a genius thing to do. They added lead to the mixture of tin bronze, and they fixed the problem with the valves. Okay, no more tiny little bleed bys, or no more dripping out through the valves. Well, that was fine, except the valves could be anywhere from 10 foot away from the pump to 400 foot away from the pump. Okay, you have considerably less pressure inside a valve or a pipe than you do inside the pump, where you're actually developing the pressure for the whole system. Well, they were making pump bodies out of this tin bronze, leaded tin bronze, and they still wound up having leaking. And that's basically only because that's where the biggest amount of pressure was being developed, by way of the impeller pushing the liquid into the piping system. And here's a picture of an impeller, and that's what those impellers, we made a bunch of them out in San Diego when I was there in 77, 78 time frame. Of all the things that I've ever made in my Navy career, those were the more, they weren't too totally hard. It wasn't one of those things where there was a lot of brain power involved to make them. But what you did have to do is, when you made the cores to form the inside of that impeller, the cores were very, very thin wall. I mean, they were not thick at all. They were sometimes they were an eighth of an inch thick for small impellers. And the most of what we used when it came to making cores was the CO2 cores, water glass cores. And even when you gave it plenty of gas, they were very, very brittle and very, very delicate. So we had to put little tiny wires all through those the cores, and I tell you, eventually it worked out. They worked, but they weren't an easy thing to make. Anyway, back to this. Okay, they found out that even if 2% of lead being added to the mixture was good enough for valves, it wasn't good enough for pump bodies. So through experimentation, they found that if you added, if you had 70% copper, 5% tin, 24.5% lead, and 0.5% zinc, you had a mixture that held quite a bit of internal pressure, and that's what they settled with. Incidentally, this, when you buy it, you would be buying high leaded tin bronze, okay? Also known in the foundries as hydraulic bronze, okay? Hydraulic bronze, 25,000 psi. You'll notice a theme here. The more lead you added, the weaker it got, okay? So there was a corresponding weakening of the outside of the strength of the metal when it came to tensile strength, but internal pressures they were able to handle quite a bit easier, okay? And as a matter of fact, lead, I looked it up just for kicks and giggles, its tensile strength is only 2,610 psi versus like the 45,000 psi of tin bronze. Now, in between this one, in between leaded tin bronze and high leaded tin bronze, is a mixture that they made, was called bearing bronze. Now, we all know why they put lead in tin bronze, what wound up being a tin bronze variation, to keep internal pressures from bleeding through. But what they also found out is that they could add, well, here's the mixture: 81 to 85% copper, 6.3 to 7.5% tin, 6.0 to 8.0% lead, and 2 to 4% zinc. What happened there? Why did they develop that? Well, they found out that if you put those two materials in there, that if you give it the time to do it, that the lead will separate. Let me back up on this, okay? You know that the bronze is going to be solidifying at about 1570 degrees. I hope I'm not blinding you by the sun coming through. The temperature that bronze is solidifying is 1570 degrees. Okay, once it solidifies, then they have to wait for the lead to solidify, and then what you're winding up with is, in that bar that you've made. Let's say you're making just a regular bar of material. You'll see on the outside of that material splotches of gray. Okay, here and there. They're totally random. They're totally different sizes, different. It's not like it, coats the outside of it with gray. It's basically just like the spots on a Dalmatian. They're all over the place and they're different sizes. They found out that if you take that material in a bar, you make a bushing out of it. The bushing will act as a bearing, and if the shaft that's spinning inside that bushing, if there for some reason the oil is not there anymore that was acting as a lubricant, that the first thing that'll happen is that the heat will develop inside between the rotating shaft and the bushing, will melt the lead. The lead will fill in that tiny little gap between the shaft and the bearing, and the bit being a liquid won't allow the shaft to grip and tear the bearing away. Now that's they used to make that alloy and then pour it into the like a billet, and used to make bearings that way. But since then, in like the 60s or the 70s, what they used to do is they would take, let me go ahead and realign you here. They would take the same material, somebody would pour it, then they would grind it into grains or dust, okay? They would then put that dust, which had the mixture of both the lead and the bronze in it, pour it into a steel mold. This is a die, something that would come together. And when the two halves came together to form this bushing that they were forming, there was so much pressure in that press that it would generate enough frictional heat that the grains would weld together. Okay, once they got done pressing it, they would release it, take it out, and you have a fully formed bushing. Many times they would have oil also added to that. So when it came down and it pressed together and those grains were all welded together, inside the voids of those granules was also deposits of oil. So once the shaft started heating everything up, the oil would expand and come and become the lubricant in between the shaft and the bushing. I thought that was very interesting when I first found out about it. Okay, let's make sure that I haven't missed anything. Showed you the dendrites, showed you the I'll also show you, showed you the dendrites, and I found a picture of what they described as a void. It looks more to me like somebody made a sound bit and then just like changed the colors of it. But this picture right here is a very good idea, or a very good representation of the voids that could be formed between two surfaces of a pump body, let's say. Okay, and that's the reason why the water would be pressed through the inside towards the outside and be a problem. Okay, now before I've covered all that, covered all that. Now here's another thing. Now when I went through the Molder Journeyman School, Molder J School, which previous to the changing to the name Molder J School was Molder C School. Okay. Yeah, this may not make any difference to anybody out there, but it was kind of a weird thing. Okay, one of our reference books that they gave us to study on was called Metallurgy by Johnson and Weeks. Okay, now there's a couple of points that they wanted to make in there. Point one: not all metals are miscible. Miscible meaning soluble. Soluble, to those of you who don't know, soluble means totally be able to mix together. Okay, and be like for instance, copper and tin. They can totally mix together and they make bronze. All right, but not all metals are soluble in the liquid state. Okay, thus lead and zinc, or in this case lead and copper, do not mix when melted together, but form two layers like oil and water. All right, now the furnaces that we used to use when I was in, I was exposed to not only the gas furnaces, but also the rocking and direct arc. But the one that we used 99% of the time when I was in the Navy was an induction furnace. Induction furnace utilized magnetic fields to not only have, here's a good idea, have molecules rub together until there was enough friction that it melted, but the magnetic fields, which were always moving, also mixed the metal. Okay, if there was anything that wasn't supposed to be there, it was mixed into the mess, and that's why just before we poured the metal, we cleaned up the inside of it and scraped off the stuff that came to the surface. In this case, for lead and copper, though, it would have been so thoroughly mixed that you wouldn't see it forming as oil and water because of that, really good mixture capability. But that does also mean that the lead was everywhere throughout the mixture, and when the bronze totally solidified, you had lead there to be able to take and solidify inside the voids. Okay, so Johnston and Weeks says that lead and copper does not mix when melted together, but form two layers. That's basically true, but it was thoroughly mixed in the induction furnace. Now they go on to say that this immiscibility is of commercial importance when making bearing bronze, in which droplets of lead are mixed throughout. It should have been throughout molten copper, like an emulsion of oil in water, and the whole is solidified. Okay, that kind of explains what I just said about how the bits of lead fill in the voids just after, as the bronze solidifies around the lead. Now, point B that they come out, two metals, however, are rarely completely insoluble. Each one dissolves some of the other, and as the temperature is increased, eventually a point is reached where any metal becomes miscible, soluble. As temperature decreases, though, each metal separates, as shown in a phase diagram that they're like lead and zinc. Okay, now this is what the point they're trying to make here is if you add enough heat, you can put, let's say, if you wanted to melt steel into lead. The problem with that theory that I just started to say, you could do it. You brought it up, the whole mixture up hot enough, you could do it. The problem is you can't go to the point where you start, flashing off or frying off the lead, because there's a point at which the lead will turn into gas. Okay, because of the heat, and will just plain burn up. If you had a ferrous material that you needed to melt into the, here's a good example. You're making a hammer. Okay, you're making an aluminum bronze hammer. Let's say for the weapons department on your ship. All right, when they're working down there, they want an aluminum bronze hammer so that no sparks can be generated around the weapons. But you're trying to make a hammer that you want to cast it around a steel handle, okay, or a iron handle. Pardon me. You want it to melt. You want it to fuse with the handle so that it just doesn't start moving around whenever you start hitting stuff. Okay. Well, if you have the handle in the mold with portion of it in the mold cavity, the odds are very good that while that stuff is molten still, the outside layer of molecules of that steel will have melted just enough that the two materials will have fused together, and that hammer won't start moving on you when you start hitting. Okay, that's an example of how you can put two metals together. Okay, so this was basically the information I was trying to. I was also going to show you the pump bodies. Here was a couple of good pump bodies, but here was a pump body that I thought was very good to show you not just the places that were machined, but how pump bodies were sent down to the machine shop and finished by the machine shop to be given to whomever needed it. You look straight down. You look down there, and these guys obviously went and sandblasted the pump body before they sent it down, because it's very nice. The outside surface is very nice, but look on the inside too. You look inside there, and you can see the inside wall of the unmachined portion of that. This is called a snail pump, because it's basically looks like the shell on a snail. And you can see where, you know, nobody would have touched that with a machine in the machine shop, and that's where the problems might have developed, having the outside be the part of the you know, the casting, and the inside not machined but being part of the casting. That's where the voids might have developed and it leaked through. Okay, so it's a good example of where it could have happened, as opposed to the one that was thoroughly machined inside and out, it looks like. Okay, well, hope this wasn't too much information for somebody. It's probably going to be an okay subject to learn about. If you have any other questions about this, you're free to ask. Okay, ask anything you want. All right. If I've just confused you, sometimes I do have a tendency just to jump around. If I've confused you, please ask, so that I can take that confusion away. Okay, these were 3 bronzes that we used in the Navy, not the only bronzes. Probably the vast majority of the bronzes that we used in the Navy. And I hope I was able to help you. This would be especially good for those of you who are actually trying to develop something and trying to figure out what materials you might want to melt and make your prize project with. So I think I've covered everything. I don't think I've left anything out for these. I've checked that, and I've covered all of those. And well, that's about it. Okay, let's see. I do have some stuff I need to make out in the foundry in the near future. Probably when it starts getting a little cooler out there, because right now I'd probably freaking pass out from all the heat in there. But enjoy this one. And for those of you who were in the Navy, Liberty Call. Though for those of you who weren't, well, I hope you enjoy. Now, as I've always said, if this is the first one you've ever seen, the first video I mean that you've ever seen that I put out, please go to video number 1. All of these videos, with few exceptions, was an attempt to go from the least sophisticated information to the most. Okay, the most basic stuff, like how it was possible that man found metal and started working metal, how to make sands, how to fix a problem with rising, with shrinkage in your castings, things like that. Or there's some of the most interesting stuff that you wanted, the basic information you want as the foundation of your knowledge before you start going up the hill. Otherwise, if you start going further up the knowledge hill, but you haven't gotten that bit of information that might fill in the gaps, you might be confused and make mistakes. Otherwise, everybody else, have a good day. Please pass the word about these videos. I don't want anybody to hurt themselves in the backyard thinking that they can pour things the bad way, and this is for safety. Okay, as the old saying goes, safety rules were written in blood. Safety rules generally aren't made until somebody's really hurt themselves badly. Okay, so always be safe. And with that, I'll see you next time. One thing I forgot to mention. I tried an experiment to try and show you how stuff precipitated out of the metal. You know, you mix up the tin bronze with the lead, and you mix it up real good, and it looks like it's thoroughly mixed. But as soon as the metal is poured into the casting and it starts to cool, the metal is no longer mixed anymore. It has precipitated out of the mixture, kind of like the precipitation in the natural environment. You'll have a lot of humidity up there. The temperature goes down. The humidity will come together in droplets and make rain. It's precipitation. Okay? I'll add the not a really good experiment. The problem with that experiment that I tried to do to show you, illustrate for you what precipitation meant when it came to the lead precipitating out of the tin bronze alloy. The problem I had was that I didn't realize that the light inside the refrigerator was going to be good enough for you to be able to see. Okay, so that was I learned something, and I know that I'll have to add, if I do anything like that again, I'll have to add more light inside the fridge. Yeah, you live and you learn. Okay, all right, see you later. Bye bye. Oh, I did mean to say that right after this, I'm going to add that film, or rather that video footage. Okay, so at the end of that video footage, and when it goes off, this is the end of the video. Okay, see you later. Bye bye. Ladies and gentlemen, we're going to have an experiment. Okay, we're going to use our imaginations. We're going to pretend a few things. Now, we're talking about bronze, tin bronze, leaded tin bronze, and high leaded tin bronze. Now, how does this work for us? Yeah, as a person who's making something in a foundry. Pardon me. Well, what happens is that when the excess lead is being added to the mixture, I mean, in the beginning, when the stuff is still in the furnace and you're stirring it, sometimes you'll stir it. You're not going to be stirring it all the time, but you'll be mixing it thoroughly. All the bronze that you've already put in there and the lead. You're not going to be able to see it or sense that it's not part of the whole mixture. It's totally mixed. Pardon me. See, it's almost like making iced tea. You got to get a supply of water. You got to get your tea, and you got to make your tea. Then you add your if you like sweetened tea, you add your sugar after that, right? Well, if you've ever done that in your life, you'll notice that once this cools down, it'll the excess sugar for this mixture will precipitate out and will fall to the bottom. Okay, precipitate out is just like precipitation in the sky. If you have too much moisture in the sky for a given humidity or a given temperature, the excess moisture will collect around each other and will turn into drops and fall from the sky as rain. Well, so anytime I use the word precipitation, that's basically what we're talking about. We're talking about how it comes out of the mixture, comes together, and it's no longer part of the homogeneous or thorough mixture of what we're making. Okay, what I'm going to do here is I'm going to test or show you, I'm going to try to anyway, show you how this works. Right now, the moisture is pretty warm. Hopefully you can see that. You'll see up here, that's the temperature of this water. I've put it through the microwave, just heated it up for 2 minutes. Okay, so what I'm going to do is I'm going to add sugar to this mixture,
And I'm going to continue adding sugar until some of it goes right down to the bottom immediately. That way I'll find that I can add no more for that given temperature. Okay, it's mixed. I don't see any more coming out, so let's add a little bit more. So far, we're making a homogeneous mixture, a mixture that's thoroughly mixed. You don't have a bunch of chunks of sugar floating in the water up here. It's absorbed totally by the theoretical mixture of tea and hot water. And hopefully you can still see that we're still doing good. Now once I get this to the point where I get a tiny little bit of sugar remaining in the bottom that won't be absorbed by this water, I'm going to try something new that I've never done before. Camera wise or video effect wise, I'm going to try and speed up this process, the cooling process. And we can look at this in speeded up mode so that you don't have to sit for a half an hour just watching paint dry. Still no liquid. I mean sugar. This is not the, am I seeing? Did I see? No, maybe I didn't. I thought I saw some crystals down at the bottom. Anyway, anybody who's ever made sweet tea, once you get the whole mixture made and you put it in the refrigerator and let it cool down so it is actually cool tea, you'll see down in the bottom of your container crystals of the sugar sitting there if you put in too much sugar for that given temperature and that given mixture. The same as for leaded, or rather tin bronze, and leaded tin bronze and high leaded tin bronze. Tin bronze doesn't have any lead in it, or at least not enough to be effective. And so if you're trying to make a material, a mixture that is going to prevent pressurized water or any other really pressurized liquid from being pushed through or in between the grains, solidified grains in the wall of the casting. I think I see some more crystals in there. I've seen a little bit. I'm not. Yep, that's very, very sugary. I don't think we need to add any more for this experiment. Okay. Now, part of this whole affair is trying to make sure that you see the time, or rather the temperature, and I'm going to try and get as close as possible. What? Yeah, this will be solid enough. Let's see if I can raise this up so you can see the bottom of this container better. Let's see. Trying to get as close as possible. The bad thing about this is that if I get this close, you won't be able to see the thermometer, I don't think. So I think that looks like you might be able to see that. All right, so what you want to watch when you're watching this, if it all works out right, you're going to want to see that this is no longer clear liquid in here. Down at the bottom, you're going to see grains of white crystals falling to the bottom as it precipitates out of this mixture, this homogeneous mixture. And you'll see how fast it happens for a given temperature. Okay? I hope everything shows up good. But see, the lens on these GoPros is more of a fisheye than a straight lens. So I was very surprised most of the time to see how well it took in the surroundings. So I will now shut up and start the new recording, so this whole recording can be, you know, put to high speed. Well, we're going to have to put that mixture inside the fridge and see if it can speed up the precipitation rate at which this, you know, water and crystal or sugar mixture will precipitate out the different crystals at a different rate. Okay, so we'll try it at a faster speed now. Okay, it was in the fridge for a long time. From the side, looking at it from the side, I couldn't really see any granules, so maybe that it didn't show anything in the camera while in the fridge. It got down as far as, what, 34 degrees, and I couldn't see anything from the side. But when I brought it out here and I looked, let's see if I can get a little light on it. You can see the bottom down there. And I'll stir it up. When it was cooling down, the the sugar that was too much for this mixture precipitated out of the mixture, and the crystals reformed on the bottom. Okay. I think you can see it in the bottom over there. Anyway, it was a good example of what I was trying to, show you. It didn't show up as good as I was hoping. I was hoping it would show you better, but I tried. Okay, on to the rest of the information.